Hello, greetings everyone. So my name is Zoltan Balazs, and I'm into offensive research mostly. I'm the developer of the zombie browser toolkit, the hardware firewall bypass tool, malware analysis sandbox tester tool. I played with some crappy IoT devices in the past, and my proof of concept remote code execution exploit code ended up running on 600,000 IP cameras. I'm pretty proud about that because usually code I write only runs on my computer, and this was code compatible with 600,000 cameras. I also invented the idea of encrypted exploit delivery via the Diffie-Hellman key exchange, and now this is recently used by the Chinese APT threat actors. And I'm the co-organizer of the Hackershly meetup in Hungary, program committee member of the Hacktivity conference, and volunteer at IoT Village. And this is a research together with Patrick Ross, and he's the co-founder of Village Idiot Labs. He's doing security research in IoT, content developer like labs, CTF, stuff like that. And he's also co-organizer of IoT Village, and he's a DEF CON black badge holder. And usually this is the part where he says something like, deal with it. So why should you listen to this presentation? If you are into emulating IoT devices, this can be interesting for you. Or if you are interested in embedded device development. Or have you ever maybe tried to debug any MIPS-based assembly? Or you want to build yourself a lab with IoT devices? If the answer is yes to any of these questions, then you might enjoy the show. If not, I recommend that you stay for the mains. But I hope you will stay, and you can find out how you can find zero-day vulnerabilities in IoT devices. So why are we doing this? Why we started this project? If you are into doing labs or CTF by visiting conferences, bringing all the IoT devices to these different events can be messy. And by messy, I mean massively messy. Like there are a lot of cables, a lot of things can go wrong, and it's just a mess, and it's a really pain to deal with it. So that's why we figured, why can't we do this with only one server where everything is emulated? Also, when it comes to vulnerability research and exploit development, this is the traditional way how you can basically emulate, not emulate, debug a device. If you want to find any memory corruption vulnerabilities and you want to figure out what is going wrong, how you can make this code execution really work. And first of all, you somehow have to root on the device. And that's just a catch-22 problem, because you want root on the device so you can find vulnerabilities. But which one is first? So it can be hard. And also, if you are into debugging memory corruption exploits, you need something like GDB server to be present on the device. But usually there are no IoT devices which have this binary. And what happens if you try to download GDB server binary on the IoT device? Well, mostly these are read-only file systems, and you cannot just do that. So there has to be a solution to this. And yeah, this can be a lot of fun if you are into this, but it can be very complicated. So we checked what's on the internet. Maybe we are not the first one trying to emulate IoT devices. And first we found Thermadyne, which is cool, but we find it a little bit bloated. There are also a lot of outdated and incorrect blog posts how you can do this manually. And we also found a very great project called ARMX. Actually, the developer of ARMX, Shaumil, is one of the hosts of this event, and he will have a workshop around his framework today. So I highly recommend you to visit that workshop if you are into IoT security. But at that time, ARMX was only for ARM-based CPUs, and it did not have any MIPS support, and we really needed the MIPS support. So we figured, okay, let's use ARMX, and let's add MIPS support to it. So I'm going to talk about architectures, the difference between virtualization and emulation, some pain around MIPS X development, some information about the kernel file systems, NVRAM, QEMU, and Docker. And there will be a demo as well. So most of you know there are different CPU architectures around, like there's the Intel or AMD one, which is using a complex instruction set. Under the hood is actually reduced one, but we don't really care about that right now. There's the ARM CPU architecture, which is a reduced instruction set. You can mostly find it in embedded devices like smartphones. Also, the latest MacBooks M1 is using ARM CPU. There's the MIPS one, which is, again, reduced. You can find it in a lot of cheap IoT devices like IP cameras. There's the PowerPC CPU architecture. This is, again, reduced one. You can find it, for example, very old Apple hardware. There's the Spark, and there are many different CPU architectures. And if you try to debug these binaries in a tool like GDB, then you can see some interesting differences between the different CPU architectures. For example, this is a hello world in Intel assembly. And because it's using a complex instruction set, you don't see too many registers. Here, these are the registers. That's not too many compared to the others we will see very soon. And also, if you look at the assembly instructions, if you have ever seen Intel assembly, these mnemonics might be familiar to you, like there's a mov call, the call, popret, NOPS instructions. These are very familiar to you, probably. So here's a hello world in ARM 64-bit. As you can see now, it has a lot more registers compared to the Intel one, because it's using a reduced instruction set. Still, the assembly is a little bit similar and familiar to the Intel one, but there are some others like this RDR, which is not available in Intel. This is a MIPS 32 assembly under GDB. Again, because this is a reduced instruction set, you can see a lot of registers, and now the assembly instructions are not that intuitive. Like, you can guess that add UI has something to do with add, or this is a move instruction, but it's not that straightforward anymore. Just for fun, I also created a hello world for PowerPC, and this is how it looks like in GDB. Again, the same story, a lot of registers because it is a reduced instruction set, but here the assembly instructions are, I have no idea what these are good for. Anyway, let's talk about virtualization and emulation. The reason I was showing to you all these CPU architectures, because most of the time, most people only live on the Intel AMD architecture. And for example, if you want to run a new operating system on your notebook, you just fire up a virtualization software like VirtualBox or VMware, and then you are good to go. But if you are trying to emulate a different CPU architecture, then this virtualization will not work for you, because virtualization software will not emulate these CPU instruction sets, which are different, as you have seen previously. QEMU is the best option we have right now to emulate these different CPU architectures. Just a show of hands, how many of you use QEMU in the past? Okay, thank you. And what's really interesting if you are into IoT emulation, that QEMU has this thing called development boards, which are basically so-called virtual machines where the hardware and the BIOS is basically emulated. I'm totally oversimplifying things here, so things are a lot more complicated, but we don't have to go deep down there right now. What's interesting that if you want to emulate an IoT device in QEMU, and you grab both the file system of the IoT device and the kernel used on it, and you want to try to run the kernel in this emulated QEMU environment, it will not work. Why is that? Because the QEMU hardware environment is different compared to the hardware environment in the IoT device. And in an IoT device, you don't have too much storage space to add support for different hardware components, right? You only have storage for that very specific hardware and nothing else. So it will instantly fail. And this means that whenever you want to emulate any IoT device in QEMU, you have to compile your own kernel. And that's going to be pretty fun, as you will see. There was a saying in the IoT world that if you want to build your own kernel, you have to just use build-root, which is a great framework for creating kernels and host file systems for embedded devices. If you want to emulate an IoT device in QEMU, the best option is if you try to use the same kernel version. Like, you can use a different one, but at the end of the day, there might be differences on how things work under the different kernel versions, and your emulation will not be the same. And if it's not the same, maybe the exploit you develop for your IoT device in the QEMU environment will just not work in the real system. So that's why you have to try to be build the same environment in your QEMU what's in the IoT hardware. Luckily for us, you can find some old working pre-built kernel binaries on the internet, for example, on this URL. And what's really nice that it is Debian-based kernels and host file systems. And after a little bit of hacking, apt-get install just works on these. And that's really good because now with build-root, you have the issue that once you build your host file system, you cannot just add any new software packages to it with apt-get or similar, because there's no such thing. You have to rebuild the whole again, and that can be a pain. But with this Debian one, you just change your repository to the archived Debian, and it will just work. But if you want to build your own kernel, for example, with build-root, well, here be dragons. What's the difference between these two options, building your own or using the pre-built ones? The pre-built ones are like almost 300 megabytes, which can be a lot compared to the build-root one. As I already mentioned, apt-get already works in the pre-built one, but not in the build-root one. And here's a list how you can make it work, for example, in your pre-built Debian environment. Just you have to start your favorite proxy on the host machine. You forward all the DNS traffic from the guest to a known DNS server. You change the DNS options in your Debian host file system to point it to your host machine. You change the proxy configuration in apt. And as mentioned, you have to change all the repositories to an archived Debian org. And that's all, and it will just work. When I was trying to build an old MIPS kernel for this project, I have seen some errors during this process. For example, here you can see a 10-year-old build-root, and this was working on a, I guess, 12-years-old Ubuntu machine. And clearly, you will run into many unexpected issues, like SSL connection was not working here because the support of Cypher suites are totally different and they have changed. Like, you cannot browse the internet anymore with these very old Linux systems. And you cannot just use a new Linux system to build an old kernel. This won't work. You have to use old Linux to build old kernel. And you need the old kernel because all of these crappy IoT devices are using really, really old kernel, like something from 2006. Also, if you are using old stuff, then all the repositories are pretty slow. And during the compilation, you can see a lot of errors. And it's always up to you to try to figure out what went wrong. It took me a lot of nights and weekends to finally make it work. And there can be mismatches, for example, in the GDB versions, that there's an old GDB server on the device, but you are using a newer client. There can be some errors and more errors and missing tools and some errors and some errors. And this is not the all. I just started collecting these screenshots in the middle of my research. So you might imagine how many errors I have seen while doing this research. And there can be some errors and other errors. I really like this one. It's an internal compiler error. I don't know whether it's exploitable or not, but looks fun. Here you can see the very old Ubuntu. I guess it's Ubuntu 8. And it starts with a kernel panic, which is not good news if you are into emulation. And here, still, you can see some other errors, and more errors, and more errors, and more errors. And this is one of my favorite ones. Like, the error states that cannot find Ninja. And I did not know at the time what Ninja is, but I found it pretty funny that this is now the errors I get, that there is no Ninja on my machine. Anyway, so as you can see, building a working and suitable MIPS kernel, if you want to build an old version, is a lot of challenge. It has a lot of challenges. Yes, so let's talk a little bit about cross-compilation. I don't have any MIPS-based desktops or notebooks at home, right? So if I want to compile any binaries for that target architecture, then I have to use my Intel or ARM or whatever desktop or notebook in order to do that. And there's something called cross-compilation to do that, which means that first I need a so-called tool chain, like binaries like GCC and stuff like that, which runs on my host machine, like it's built for the Intel instruction set, but it can compile binaries for the target ones. That's what is called cross-compilation. And most of the time it works, but there will be some errors and issues you have to figure out while doing that. You have also the option that if you have a working, for example, MIPS emulated environment in QEMU, you can try to compile natively something in it which does not involve cross-compilation. But I promise that it will be really, really slow. And if there is any error during compilation, trying it again, it's a lot of pain. So I don't really recommend you to do that. So as I already mentioned, most of these crappy IoT devices, they use really, really old Linux kernel. For example, a very popular kernel version in IoT devices is 2.6.32. Maybe it's from 2006 or something like that. So you can guess how many vulnerabilities are in those devices already. But if you have an IoT device which has a really recent kernel running on the MIPS architecture, then you are lucky, because if you just follow, for example, this tutorial, you can easily get one which is working right away. Yes, and a little bit of note on static versus dynamically linked binaries. As I mentioned, if you go down the build root way, you will not have anything like opt-get install or similar. But if you forgot to add any binary to the image, you can still do that by statically compiling binaries, which means there will be no dependencies. All the dependencies and shared libraries are inside the binary itself. So you can just drop your binaries and they will ready to go, and you can use it already. For example, for this project, we have compiled GDB server, Netcat, Socket, Telnet daemon, stuff like that. If you are into IoT research, you might need these tools. So, as I mentioned, if you want to cross-compile stuff, you have a little bit of different options how you can do that. For example, there's build root, as already mentioned, OpenWRT, which is based on build root, CrossToolNG, Muscle, Code Sorcery, CodeBench, DuckCross, Debian CrossTools. I have tried all these different options, and what worked for us the best is build root is really good for building the host file system. But if you want to cross-compile static binaries, I recommend the Muscle cross-compiler for that. Okay, but after a lot of trial and error, you will be greeted with this nice login prompt that now I'm able to run MIPS-based emulation under QEMU. And I only needed these 6 different VMs in order to get there. Now a little bit about single binary and full system emulation. This whole project I'm doing on top of ARMX is about full system emulation. And usually you need the full system emulation to find vulnerabilities in IoT devices. But you might be lucky, and it's possible that you just copy a single binary from the IoT firmware, and maybe you just copy some config files with it, and you might be able to run this single binary on your host machine without this whole full system emulation and without the kernel and host file system and stuff like that. For example, you might know the researcher Azaria. She has a very nice tutorial on how you can do this on the ARM framework. And if I just changed basically in her tutorial the words ARM to MIPS, and everything just works. So if you want to emulate just a single binary on your host machine, you have to install all of these packages. Then using the GCC cross-compiler built for the MIPS architecture, I can build static binaries, and I can also build dynamically linked ones. And what's really nice in this QEMU user mode emulation, that everything will just work, as you can see on this screenshot. So on the top, you can see that this is the C source code for the hello world. And here I'm using creating the static binary and the dynamically linked one. As you can see, the file command correctly tells me that this is a MIPS binary, the statically linked one, and the dynamically linked one. And I'm using Intel AMD architecture right now. This is the host machine. But still, I can do this, like executing the binary without knowing that it's a MIPS one. It will just work, and the QEMU user mode package is doing this whole background task for you, that it will just work. Unfortunately, the dynamically linked one will not work by default, but we are used to this, that things just don't work. Luckily, there's this very easy fix how you can resolve it. But this is pretty nice. I think that by default, if you only are interested in emulating a single binary, is that easy. Now let's talk a little bit about the file systems. For the MIPS architecture, there are many different CPU versions, and historically some of them are compatible with each other, some of them are not. Regarding the file system, when you are into the emulation of your IoT device, the way it works is that first you need the QEMU emulation framework, which will start the kernel, for example, for the MIPS architecture, and then you will run the basic host file system, which is just a basic Linux image with all the tools you need. And after that, you have to copy the firmware files from the IoT device. And once you have a running operating system with your generic host file system, then how you can basically start the IoT device is that you change your directory into the directory where your IoT firmware is. You use chroot, and then you can kickstart the boot process. This is a little bit of confusing how these all are connected together. I'm really sorry for that. But basically what you do is that you first start your generic host file system, and once it's up and running OS, then inside that you run your emulated IoT firmware in a sage-rooted environment. All right. I also created some guides and notes on how you can build this host file system, but I'm not going into details into that. If you are interested, just download the slides afterwards. And there's only one thing remaining I have to explain to you, and this is called the NVRAM, or the non-volatile RAM. Traditionally, IoT devices have read-only file systems, and the reason behind that, because it can be a lot cheaper to have a read-only file system, and also the lifetime of the device can be a lot more by years if you are using a read-only file system. Like, you know, HDDs and SSDs, they usually fail after 5 or 10 years, and these IoT devices are built for a much longer lifespan. But if you only have a read-only file system, then how you can store any of these configurations? For example, let's say you have a home Wi-Fi router, and you want to change some of the settings of it, like the Wi-Fi SSID or the Wi-Fi password or the IP addresses. In order to store those configuration options, you will need this NVRAM. And whenever you want to emulate an IoT device, you also have to take care of the emulation of this NVRAM device, because by default, QEMU is not providing this for you. And first, if you already hacked the IoT device, you have to somehow extract all the NVRAM parameters. Like I mentioned, the SSID and IP address and all these different configuration parameters, and then you have to emulate them inside. And just a little bit about the QEMU VMs. Things can be complicated if you are not used to QEMU. For example, by default, it will give you an interface, a network interface, which does not really work how you expect network interfaces. But this is due to that QEMU can be run without root privileges. But if you run QEMU with root privileges, then you have the option to use, for example, tap interfaces which will work the way you will expect, for example. Also, as I mentioned, whenever you are into vulnerability research and exploit development, you want to achieve that the whole memory layout of the device is exactly the same as it is on the real device. And for example, what this practically means for you, that whenever you compile your kernel, you have to use the same kernel compilation options as it was used in the IoT device itself. Also, because you want to debug your IoT device in this emulated environment a lot, you have to take care about how you access this emulated environment. For example, you have to expose your SSH ports or GDB server and stuff like that. Okay, and when we started this whole journey with the ARMX project, there was two options available. There were some code on GitHub which you can try and hack yourself onto your Linux device, but there were no instructions how you can do that. And there was an Alpine Linux virtual machine. And none of these options were user-friendly, I have to say. So me and Patrick figured out, okay, let's migrate this whole ARMX framework into Docker. And this means that we are adding one more layer in top of everything. So now we have the host machine, then we have the Docker container inside, and the Docker container will run the QEMU emulation inside that, and QEMU will start the so-called host kernel and the file system. And as I already mentioned previously, this already working emulated OS and file system will kickstart the siege-rooted IoT environment, which environment already includes your target binaries which you want to attack or research, for example, the web server. And because you want to debug your stuff, the SSH server and GDB server and all these servers to debug your application will be on the so-called host kernel file system. But don't confuse this host to the top outer layer of host, because we are so many layers deep down, it's really hard to what do you call a host and what's a guest. You can get lost easily, like I did many, many times. Alrighty, and let's see this in action. Luckily, I already have a recorded video for you, so I'm not going to do a live demo here. So let's see how this works. So on the top, I'm starting the ARMX Docker binary, which will kickstart the QEMU environment. And on the bottom, I'm starting the Docker shell. And here, this is a camera I have at home. And now the kernel and the host file system, generic host file system matching to this camera starts. This is still not the IoT device itself. And now I can start the siege-rooted environment and kickstart the IoT device. As you can see, there are a lot of error messages, and it's sometimes really hard to figure out which error messages are interesting for us and which are not. But as you can see, stuff works right now. For example, if I'm checking the CPU info, you can see that I'm running MIPS emulated environment. And I can also check what kind of services are running on this device. And as you can see, Telnet is running on this IoT firmware, and as it quickly turned out, this very cheap IP camera has a built-in telnet server with the username admin and very secure password 12345. So it's really hard for any type of hacker to hack this device, but there are also other interesting ports which are running here. And now that I have a running emulated IoT environment, what's really nice that I can very easily connect to any process inside the QEMU environment, and now I have a fully working GDB session where I can see the states of the register or the code execution flow, and from now on it's a lot easier to develop any type of exploits if I'm interested into that. All right. So what are the next steps we want to achieve with this project? The NVRAM is a little bit buggy at the moment, so we have to still work on the NVRAM emulation part. If we have time, we will implement some CI/CD solution where you only provide the firmware file to the framework and it will automatically build everything for you. And we are doing this whole because we want to pay forward to the security community. And we really do hope that frameworks like this can help to put pressure on the vendors to make their IoT devices safer. And we are releasing all of our code in open source, so everyone can contribute. And we also hope that, for example, bug bounty hunters can use these frameworks to find more and more vulnerabilities in the devices. So you can find our project on the link on the top. But due to how fast Xiaomi works with his emulation framework, I have to admit that our solution is already outdated. We also pushed the pull request to the RMix framework, but what really happened right now is that Xiaomi implemented his solution to support MIPS emulation in his RMX framework, and he renamed his project to MIPS X. So if you want the real deal right now, the best option you have is to check out his project repository and use that version, because that will be updated and supported more frequently. And last but not least, don't forget that Xiaomi will show you his whole framework, and he will go into the different details of this framework today. You just have to visit the break track at 2 o'clock, and you will see a 2-hour presentation about his framework. So that's all, folks. That's all I wanted to share with you. Thank you for your attention, and if you have any questions, please use the app to do that. Thank you.